Okay, so in this video, we will consider the topic called higher derivatives. As you will see, this is a very simple idea, but it's not obvious why it's useful. And this will be the topic of our next video, looking at applications of the idea of higher derivatives. In this video, we'll simply look at examples, figure out what are higher derivatives, and in the next video, we'll look at why these higher derivatives are actually really important and really useful. Let's take a very simple example. Suppose we take the function y equals, let's go with sine of 3x squared. Well, y is a function of x. It is a differentiable function of x, so we can differentiate. So we can write y prime. This is the same as the derivative, so dy over dx. And that's the derivative of sine of 3x squared. So we apply the chain rule. The derivative of sine is cosine of the same argument, 3x squared. But that's just the derivative of sine times the derivative of the argument, which will be 6x. So you see that the derivative of sine of 3x squared is simply 6x cosine of 3x squared. And so you notice that y was a function of x. The derivative is also a function of x. So you say, well, why not differentiate the derivative? So here's how we'll write this. So we use a single prime for saying that we have differentiated y one time. Now we'll differentiate a second time. So we'll write y double prime. So it's not y to the 11th power. These are primes. So it means that we differentiate y not just the once, but twice. So this will be the derivative, d over dx. We differentiate y prime, which we can also write as the derivative of, you can replace y prime by dy over dx. So we differentiate the derivative of y with respect to x. And there's a way of writing this. If you write it this way, you have the derivative of the derivative of y. So we can write it in this way. We have d, so we write d squared, dx, dx, dx squared of y. So again, all this means is you differentiate the derivative of y, and you can write it in this way. You think of it as d over dx is the derivative, but now we're saying we differentiate twice the function y. And now let's compute this. This is the derivative of the derivative. So here we have 6 times this, but 6 is a constant multiple, so it will stay up front. And now we have to use here the product rule. This is x times cos of 3x squared. By the product rule, the derivative will be the derivative of x, which is 1, times the second function, cosine of 3x squared, plus the first function, x, times now the derivative of the second function. The derivative of cosine is negative sine of the argument 3x squared, chain rule, times the derivative of the argument, which is 6x. We can simplify a little bit. This is 6 times cos of 3x squared. Here we have 6x, x is 6x squared. There's a negative, so negative 6x squared times sine of 3x squared. And now we have the so-called second derivative. This is the first. derivative, which means that we have differentiated y only one time. Now we have taken the derivative of the derivative, so we have differentiated y two times. And this is called the second derivative. And you say, well, why stop here? Why not differentiate the second derivative? So why not differentiate the function three times and have the so-called third derivative? Because the second derivative, the derivative of the derivative, is also a function of x. Let's do it one more time so we can write y triple prime, which we can also write using this notation as we differentiate, so d over dx, three times we'll have d over dx, d over dx, d over dx. Of y, which we can write more concisely as d cubed, over dx, 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 dx cubed of y. So we're saying differentiate y with respect to x, but three times. Y triple prime. Let us now differentiate, but as we have said, this is the so-called third derivative. And those are the so-called higher derivatives. You see, the first derivative is just that, the first derivative. The second derivative is a higher derivative because it is the derivative two times. Then the third derivative is also a higher derivative because we differentiate, simply put, more than once. Let us now differentiate. So if you take the derivative of the second derivative, you get the third derivative. Let's see, 6 is a constant multiple, so it will just stay there. Times the derivative of this. Derivative of cos of 3x squared will be negative sine of 3x squared times chain rule 6x. Minus 6 is a constant multiple, so it will stay there. Here we have a product between x squared and sine of 3x squared, so we use the product rule. Derivative of x squared is 2x times the sine of 3x squared plus x squared times the derivative of sine of 3x squared, which will be cosine of 3x squared, times the derivative of the argument, which is 6x. And there you have it. We have now the third derivative of y. We can simplify a little bit. We can factor from both of these terms a 6. So we'll get 6 times 6 up front, which is 36. And if we factor the 6 of both terms, let's see what we're left with. We'll have here a negative x sine of 3x squared. This will be negative 2x sine of 3x squared. This will be a negative 6x cubed cosine of 3x squared. We can simplify a little bit more. If you notice, we have negative x sine of 3x squared, negative 2x sine of 3x squared. So this will be simply negative 3x sine of 3x squared. So negative 3x sine of 3x squared. negative 6x cubed cos of 3x squared. Well, we have two common terms. There's a negative 3 that can be factored from both of these. And there's also an x. Well, negative 3 times 36. Negative 3 times 30 is negative 90. Negative 3 times 6 is negative 18. Negative 90, negative 18 is negative 108. Also a factor of x, so x. And now we are left with, well, we pulled out the negative 3x, which leaves us with a sine of 3x squared. We pull that from here a negative 3x as well, which will leave us with a positive 2x squared times the cosine of 3x squared. Right? Multiply this by negative 3x and you get negative 6x cubed. This is as simplified as can be, and so we have now the third derivative of the function y, which was sine of 3x squared. And you can keep going. Why stop there? Differentiate this one more time, you'll have the fourth derivative. Differentiate again the fifth derivative, and so on, and you can differentiate as many times as you want, so in general you can get the nth derivative of the function. And those are the so-called higher derivatives. So here's how we can write the nth derivative of the function. This is a summary for the notation. So the nth derivative of y equals f of x is denoted by, and again the nth derivative, where n is a positive integer, just means differentiate the function n times. So if n was 8, you would differentiate the function 8 times. And here's how we denote it. Now, if you look back, the prime notation is actually only nice up to the third derivative. Then it becomes extremely inconvenient, because then you have y prime, y double prime, y triple prime, y quadruple prime. So if you use this notation and I say find the, say, 10th derivative, you'll have y prime 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 10 times. Horrible notation. This notation is actually very nice, because we simply write d over dx, and we put an exponent top and bottom, and that is the number of times that we are differentiating the function. So this is a really good notation. So only ever use the prime notation for the derivative for the first, second, or third derivative. Beyond the third derivative, use this notation, and we'll see another also very nice notation. So the nth derivative of the function y equals f of x is denoted by, as we have said before, we can write d over dx. This is the action of differentiating. We differentiate n times, so d n dxn of y. So this means differentiate with respect to x the function y n times. You could also write really nicely simply y with, and here's where the notation is a bit subtle. If you write y to the n, this means the nth power of y, therefore y times y times y n times. But if you put round brackets around the exponent and you say y, open the bracket, n, close the bracket, this also means the nth derivative of the function. So it's as if you had here n prime, so prime 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 n times. You can also write using, well, replacing y by f of x, you can write f, open the bracket, and in the exponent, which means differentiate the function f at x n times. So 3 different ways of writing the nth derivative of the function y equals f of x. And remember again that this means you do the derivative of the derivative of the derivative of the derivative of the function y, and we differentiate n times, so it's d over dx of d over dx of d over dx of y, exactly n times. And those are the so-called higher derivatives when n is 2, 3, 4, and so forth. So when n is 1, it's the first derivative. When n is 2, the second derivative. And in general, this is the nth derivative. One simple remark: what if we plug in here n equals 0? Well, think of what that means. We're saying differentiate the function f 0 times. If you differentiate f 0 times, you simply get f of x. So this also makes sense if n is equal to 0. If you don't differentiate the function, you get the function back. So this is just a small comment. Let's do 2 more examples. So here's the first one. Let's ask for the, let's say, find. Let's go with the 5th derivative. So this is a higher derivative. So find the 5th derivative of the function y equals, let's go with e to the x squared. So to find the 5th derivative of this function, we have to differentiate the function 5 times. Let's find the first derivative. And again, up to the 3rd derivative, we can use the prime notation. Then we'll use a better notation with the little exponent in the bracket. So we find the first derivative, y prime. Differentiate this with the chain rule, you get e to the x squared times the derivative of x squared, which is 2x, which you can write as 2x e to the x squared. So we now have the first derivative. Find the second derivative, y double prime. So differentiate the derivative to get the second derivative. 2 is a constant multiple, leave it up front. And now we differentiate x times e to the x squared. So we'll use here the product rule. Derivative of x is 1 times e to the x squared plus x times the derivative of e to the x squared, which is e to the x squared times 2x. Let's see what we get. We can factor from these two terms in e to the x squared. So we'll have 2 e to the x squared, and we'll be left with a 1 here and a 2x squared here. So 1 plus 2x squared. We can write this, of course, as 2 times 2x squared plus 1 times e to the x squared. Let's differentiate one more time to find the third derivative, y triple prime. And this will be the last time that we use the prime notation. 2 is once again a constant multiple, so leave it there. 2 times. We have once again the product, so we use the product rule. Derivative of the first function, 4x, times the second, e to the x squared, plus the first, 2x squared plus 1, times the derivative of this function by the chain rule, e to the x squared times 2x. Once again, we can factor common multiples. We can factor in e to the x squared. We can also factor a 2x. times, then we were left with, if we factored 2x from 4, we're left with 2, plus, everything here was factored except for this term, so plus 2x squared, plus 1. So in the end, well, what do we have? We have a 4 up front, e to the x squared. And here, if I leave the x up front, we'll have e to the x squared times x times this. That will give us two products. It would give us the extended product rule, and that's a bit too complicated. So here, we'll bring the x back in. So times 2x squared times x is 2x cubed. 2 plus 1 is 3 times x plus 3x. And this is good because it will give us only a single product, which will make the next differentiation a little simpler. So we have then 4 times 2x cubed plus 3x times e to the x squared. Let us now find the fourth derivative. And now we'll use the notation y, 4 in the exponent, but in round brackets. So to find the fourth derivative, we differentiate the third derivative once. 4 is a constant multiple, it stays there. Once again, we use the product rule. Derivative of this, 6x squared plus 3 times e to the x squared plus 2x cubed plus 3x times the derivative of e to the x squared, once again by the chain rule, e to the x squared times 2x. Let us factor. The only common factor is an e to the x squared. And we are left with 6x squared plus 3 with the first term. Let's multiply out these two terms. We'll have 2x cubed times 2x. This will give us 4x to the 4. Plus 3x times 2x plus 6x squared. Let's simplify. We have 4 times the polynomial. 4x to the 4 plus 6x squared plus 6x squared plus 12x squared. And finally, the constant term plus 3. And this is all times e to the x squared. Now we catch our breath and we say one more time. We wanted the fifth derivative, so if you differentiate the fourth derivative, you will get the fifth derivative. Y to the 5 in the round brackets. We have a simple product rule. 4 is a constant multiple, so it stays there, times the derivative of the first function, 16x cubed plus 24x times the second function, e to the x squared, plus the first function, 4x to the 4 plus 12x squared plus 3 times the derivative of e to the x squared, once again by the chain rule, is e to the x squared times 2x. We could simplify by factoring e to the x squared, and x from the two terms, and then combine. At this point, I'll leave this up to you. That's just algebraic simplification. And we now have found the fifth derivative of the simple looking function e to the x squared. And you see that depending on the function, the higher derivatives can be quite complicated. As we keep differentiating e to the x squared, the derivative will get more and more complicated. Let's do one last example of a higher derivative finding the, say, second derivative if we have an implicit differentiation problem. So here's the example. So find the second derivative. So find d squared y over dx squared, which is just, again, the second derivative of the function, if, say, x to the 5 plus xy minus y cubed is equal to, say, 1. So we have here a curve in the xy plane defined by this equation, and we want to find the second derivative of y. So let's use implicit differentiation. Both sides, if we think of y as a function of x, both sides are equal as functions of x. So we differentiate both sides with respect to x. The left-hand side is x to the 5 plus xy minus y cubed. This will be the same as the derivative of 1. Let's differentiate both sides. The derivative of x to the 5 is 5 x to the 4 plus, here we have a product, so we use the product rule. Derivative of x is 1 times y plus x times the derivative of y, which is dy over dx, minus the derivative of y cubed by the chain rule is 3y squared times dy over dx. And that's equal to the derivative of 1, which is simply 0. Let's isolate the dy over dx, so send both of these onto the right-hand side of the equality. So we are going to have 5x to the 4 plus y is equal to, I will factor already the dy over dx. The negative 3y squared will become a positive 3y squared. The positive x will become a negative x. And we can finally solve dy over dx for the derivative of our curve by dividing across by 3y squared minus x. So this will be 5x to the 4 plus y over 3y squared minus x. So we now have the derivative, the first derivative of our curve, as a function of x and y. It is 5x to the 4 plus y over 3y squared minus x. Well, if we want the second derivative, we simply have to differentiate the derivative, and we'll differentiate this, and we'll obtain the second derivative. What we'll get will be a little messy. We won't simplify it. The point is to understand how you would be able to get to a point where you can then simplify algebraically the second derivative. So let us do so. So as we have just said, to find the second derivative with respect to x of y, we must simply differentiate the derivative. If you take the derivative of the derivative, you have taken the derivative of y 2 times. Well, we can make a substitution. We want the derivative of the derivative, dy over dx, but we have just found it. So we replace dy over dx by its expression, which is 5x to the 4 plus y over 3y squared minus x. Well, to differentiate this, we need to use the quotient rule, as we have a quotient. So let's do so. It will be the derivative of the numerator, so 10x, plus the derivative of y with respect to x, so plus dy over dx. That is the derivative of the numerator times the denominator, 3y squared minus x, minus, now we flip the two rows, so minus the numerator, 5x squared plus y, times now the derivative of the denominator. Sorry. Here be careful that there is a y, so complete the chain rule, you'll get 6y times dy over dx minus the derivative of x, which is simply 1, and this is all over the denominator all squared. So 3y squared minus x, the whole expression squared. So now we have the second derivative. We took the derivative of the derivative, and here's what we have. The only question left here is, could we express this in terms of x and y only, and not also dy over dx? You see, we have found the second derivative, so as far as the differentiation is concerned, we're done. But you see that the second derivative happens to be a function of x, of y, but also of dy over dx. So you see, well, how could we get rid of this? Here's a dy over dx. Here's a dy over dx. The question is, do we know dy over dx is a function of x and y? The answer is, sure we do. We have just found it previously. So the next step would be to take the expression for dy over dx as a function of x and y and substitute in here. So replace this by 5x to the 4 plus y over 3y squared minus x. And do the same thing here. Replace the other dy over dx by 5x to the 4 plus y over 3y squared minus x. Then you'll have to simply algebraically simplify the expression. And at this point, we'll stop there, because all this will be is just a little bit of messy algebra, and I will leave this up to you. And this is how you would find the second derivative as a function of only x and y by replacing wherever you have a dy over dx by what you have previously found. And that completes our discussion of higher derivatives. So you see, it's pretty straightforward. You want to find the nth derivative of a function, differentiate n times. There's nothing more to it. So it's a very simple idea. The question is, why do we care? Why is this useful? Well, this will be the topic of our next video. We will consider now trying to sketch the graphs of functions by hand, and we'll realize that the first derivative is very useful, but is not enough. We also need to use the second derivative. So in our next video, we will look at why is the second derivative important in helping us sketch the graphs of functions. And you may ask then, okay, why do we bother with finding the third, the fourth, and even higher derivatives if we will only use the second derivative? And this is what you will see next semester when you take integral calculus. At the end of the term, you look at applications of higher derivatives beyond the second derivative. And you'll get to see a really, really nice application of these third, fourth, fifth, and beyond higher derivatives. But for us, in this course, we'll only need the second derivative.